Last class we took a look at what the requirement specification engineering process was like, and we saw that one of the ways by which requirements can be specified was by using natural language or an English like syntax. But there are also problems with that approach, and we saw some alternative approaches such as graphical notations, templates and forms that can be used in a structured approach, and lastly we briefly got introduced to mathematical forms of specifications. In this lecture we are going to go deeper into formal methods or using mathematical notations in order to specify requirements of a system and how they can be used for building the rest of the system. So what exactly is a formal specification? A formal specification, as the name implies, is a technique for unambiguous specification of software to be built. Right? One of the problems that we saw by using the natural language representation was that even though it is the language of choice largely for requirements of today, it has several problems associated with it. One of the problems is that it gives rise to several ambiguities when the person who reads the document typically ends up interpreting the document in his or her own words. Right, and these ambiguities are going to vary from person to person, as a result of which two different people reading the specification can get two different ideas of what the system is to perform. The natural language does not also serve as a good means for modularizing the software. So if a bunch of English statements are written, it could be that these cut across very many different modules. They are not related statements, for example. There is no way of ensuring that all these statements are at the same level of consistency or same level of detail, and we saw an example of that in the last lecture. So with all these problems, it kind of behooves us to look for methods that give us a more structured or a formal means of writing down the specifications of software, and that's what we're going to look into. So just to summarize on the problems that can occur with natural language specifications, linguistic ambiguities is one of them, English by its very nature. The implicit domain specific knowledge, which is often not represented because the context is often assumed in the case of an English specification. So if you were for example talking of insulin pumps and things like that, the context of the medical world in which these terms are going to be used is not necessarily well defined, and there can be certain assumptions that are made which will cause a person down the line to reading the specification to not necessarily understand it in the right way. There can be a lot of inconsistency between different phrases. There can be grammatical errors in the document itself, which can lend itself for a different interpretation. Also, it is very hard to reuse natural language specifications. So for example, if I wanted to reuse the specification of a GUI screen for another system which was actually being built for a completely different purpose, it would not be very easy to do so. And the prototyping cycle is quite long in the case of natural language specifications, simply because a human has to read the specification, has to interpret and understand the specification, and then work on prototyping. Whereas certain alternative techniques can be made available, such as code generation, for example, which is one of the goals of formal specifications. So just to give an interesting example, here is a case study, if you will. It's not really a formal case study, but a situation which depicts the need for formal specifications. So this slide actually shows what is the project that is what is the project that is proposed by the project sponsor. So this is the client. He wants to build a piece of hardware in this particular case, and this is what is shown as being proposed by the project sponsor. And what we'll see in the next successive set of slides is really how this can get twisted out of shape when you're using natural language, and what comes out as the end product really has not much of a relation to what is really being input to the whole process. Right? So the second step is that somebody has to specify this in the project request, and right there, due to natural languages being used, you can see that the initial specification of what the project sponsor wrote out has kind of been malformed a little bit. Right? As we go along, we are going to see that the senior analyst who read the specifications interpreted it completely wrongly in this case, and so for example, he may have looked at the flexibility of the rope and then designed a really flexible system, but that's not, it's not a swing, which is what is wanted in the first place. As we go along, we see that this thing is evolving in a different way, because the programmers who are the next step in the software development process are going to interpret the analyst statements yet very differently. Then finally they installed it at the user site, and this is how it looked. But what the person who was going to use this actually meant was he simply wanted a tire hanging from a piece of string off of a tree, so that his child could play swing on this piece of tire. So what this is trying to depict is the need to be able to carry through a set of requirements, or carry through a set of statements all the way from the requirements part of the software process through the analysis part to the building part of the implementation part and the installation part finally, and all of these need to reflect what the user originally asked for in the requirements document. And this is why it is important to have a means of specification where you're going to be able to verify it formally, maybe using tools, and then ensure that you can go from phase to phase, such as from the requirements to the analysis phase, from the analysis to the design phase, from the design to the implementation phase, and so on, without losing track of what the original requirements were meant to be. So formal methods, which is a broader set of methods than simply doing the specifications themselves, is part of a, so the specification is part of a broader collection of techniques called formal methods, and most of these are based on some kind of rigorous mathematical specification of the software, right? And the formal methods includes 3 to 4 steps typically. The first one is the formal specification itself, where the software requirements are laid out and then specified by the programmer analyst in a formal method using either algebraic steps, as we shall see later in this presentation. The second step is that of specification analysis and proof. So the specification can be checked for consistency, which you cannot do with the natural language kinds of specifications. The third step is one of transformational development. And what this really means in this particular case is that typically if you take a look at the software development life cycle and the process, you go from requirements to analysis, and you go from requirements analysis to design, and each one of these steps needs to have a certain degree of continuity in between them. So there is the output of one phase. So for example, the output of the requirements phase is a requirements document that is being fed into the analysis phase. The output of the analysis phase is an initial or a very high level design of the system. That is fed to the design phase. The output of the design phase is a detailed design of the system, which can then be taken and implemented by the programmer or the developer. Now, this development process typically has as its interfaces between the various phases documents, right? So analysis document is created. The document is then read by the designer. He produces a design document that is read by the developer. He then produces an implementation. Now what this lends itself to is what developers and what analysts and these people end up tending to do is they end up trying to interpret what has been written down on a piece of paper or within a document, and that interpretation can vary from person to person. So if there were a means to take the requirements, verify it, and then transform the requirements automatically into code, which is the end product of the software development process, that would essentially ensure that we retain the continuity between the various phases of the software development lifecycle. And that is what transformational development means. What it's trying to focus on is the idea of taking a requirement specification which has been specified formally, verifying it for consistency, then generating the design from it, allow a human to verify the design, and then generating the code from that point onward, generating the test from the specification and testing the code against the specification. All of this can be automated or it can be controlled through machine tools which will essentially ensure that the human ambiguity that is brought into the picture because of persons reading the specification or reading the design document and then producing analysis or producing implementations, and that variability will get taken away. And every time there is a consistent transformation that is taking place from a specification to a piece of code, which is really what we are after at the end of the day. And finally, program verification refers to checking or testing to make sure that what we have built indeed conforms to the specification that was given to us in the first step. And program verification is also can be automated when we use formal methods, because test cases can be generated from the specifications themselves, and the test cases can then be applied against the final end product of the process, which is a code. And this can help us verify whether it indeed conforms to the specification that was set out at the beginning of the process. Now, one of the things, caveats I guess, that we have to keep in mind as we go along this path is that formal specifications or formal methods in general have not taken off the way that they were predicted to, say way back in the late 70s to the early 80s. A lot of hope was being held out at that point in time that these would become mainstream software development methodologies, but so far they have not happened, and we should kind of take a look at some of the reasons as to why this is the case before we get into the techniques and the hows of how we're going to end up doing this. The first reason for this is that other software engineering techniques have been catching up, right? Catching up with respect to increasing the efficiency as well as decreasing the number of errors that were introduced in the software development process. Right? One of the advantages of the formal specification is that humans cannot introduce errors into this process because they are not really as involved as in alternative software development methodologies or practices. Right. So a lot of other techniques have come up, especially process-based techniques that can help control system quality and keep it under check. And so the kind of the need for formal methods has come down, but that's not really a primary reason for this. The more important reason is that formal methods have kind of failed to scale to really large systems. So in order to formally specify a medium-sized enterprise class system like an ERP system, it would take quite a bit of mathematical rigor and expertise, which is largely absent from the industry today, even today, let alone 20 years ago. As a result of which, formal methods have primarily been shied away from, although they have been applied in critical systems, which is where we'll see the main applicability ends up being. So the scope is kind of limited. They are not very well suited, for example, also to analyzing or specifying front-end GUI based systems. They are primarily very good at back-end system specification, and a lot of the systems today are GUI driven. Also, market factors and market changes is something that we cannot underestimate, has dictated the time to development or the time to market be really short because of the competition around us. And the need for getting these systems into production very, very fast has kind of driven that, and formal methods take quite a bit of time to develop because it is focused on doing the job right in the first go, as opposed to an incremental method of evolution where errors or bugs are found and fixed as the system evolves, rather than a system being perfect from the word go. So the use of formal methods, because of all these reasons, has a certain limited practical applicability at this point in time. Although the principal benefits are primarily in the areas of reducing the number of errors, and they are primarily applied in the area of mission critical systems. So a good example would be software that runs avionics. Software that runs the large planes that you fly in today is all formally tested at certain parts of the software, at least the smaller parts, which are very, very critical. So something like that controls the rudder, or that controls the braking and so on. The critical pieces of software are essentially built using formal specifications and formal methods, whereas the rest of the system is built using regular software engineering practices, and then these are put together. So specification where does formal specification fit into the software development life cycle would be the next question that we would tend to ask. And specification and design, although inextricably mixed with each other, formal specification falls somewhere between the requirement specification stage, which may be done with natural language first just for the sake of convenience, and between the design stages. And it is actually an analysis methodology, if you will, more than a requirement specification methodology. As we shall see on this slide, the first step is really that of the requirements definition. That is something that is done by the user, that is typically still done in the natural language and that cannot be avoided. This then translates into a requirement specification. Now, it is possible to argue that the need for a requirement specification step can be avoided, and we can straightaway jump into the formal specification step, but it's generally not recommended that we do that. And once we get into the formal specification step, then the high level design can actually be generated out of the formal specification, and different system models can be driven off of the formal specification. So for example, UML models can be generated out of the formal specification. Other test models, for example, can also be generated out of the formal specification. So specification techniques for formal specifications largely fall into two categories or two classes, if you will. The first one is called an algebraic approach, and the second one is called a model based approach, and there are different languages, techniques and tools that fall into each one of these categories. The algebraic approach essentially focuses on specifying the system in terms of its operations or its interfaces, if you will, and the relationships between these various interfaces. Whereas the model based approach concentrates more on specifying state models and specifying the system using mathematical constructs such as sets and sequences, right. So the operations are mainly being defined as modifications to the state, and the state is central to the model based approach, whereas the operations themselves or the interface specifications and axiomatic specifications are those that are central to the algebraic approach. Because both of them do have the formality really is introduced by the notion of axioms in the case of the algebraic approach, and in the case of invariants in the case of the model based approach. So that degree of similarity exists between these two approaches, but the difference mainly is that one is state based. The model based approach is primarily state based, whereas the algebraic specifications approach is primarily based on the operational signatures of the various functions that go to make up the interface of the module that is being specified. So formal specification, there are several languages that have evolved over a course of time, as can be seen from this slide, and we have kind of categorized the different languages into 4 different categories. The first category is that of the sequential specification languages that focus on sequential programs and are algebraic in nature, and that is covered here. And the two primary languages in this category are Larch and OBJ. And when you move to concurrent languages, there are fewer languages in this case using algebraic specifications, and concurrency essentially introduces the notion of multiple modules working together at the same time, whereas model based approaches that are quite popular are Z and VDM that you might have heard of before already, and CSP and Petri nets in the case of concurrent approaches. So one of the things that we have to be aware of before we delve into the details here is that formal specification involves investing a lot more effort up front, because you are taking time to mathematically model the constructs, and that takes a lot more time in the early phases of software development, whereas it will ease out the later phases because transformational development is the focus of formal methods, whereas hand based manual development is really the focus of other software engineering practices. So it also ends up reducing a lot more errors over the life cycle of the software because of the verification steps that are done up front and the consistency checks that are performed up front. and the inconsistencies and the incompleteness that may exist within the specification. For example, the lack of a context defining a certain term, they can be removed upfront early in the life cycle and can be restored or resolved. So in terms of the overall life cycle, if we take a look at how the cost gets spread out, here's a slide that shows the comparative differences between the amount of time that is spent on specification versus design, implementation, and validation with and without formal specifications. It can clearly be seen that in the case of formal specifications, a lot of time is spent in the specification itself, and not as much time is spent in the design and implementation because it's transformational in nature, and validation also is fairly simple to do. Whereas in the case of building software without the use of formal methods, specification doesn't take a whole lot of time because it is done using natural language, it's done fairly quickly. Whereas the design and implementation, the validation phases, the ones that end up taking the most time. And one of the things that is not shown here is the fact that the number of errors that get introduced in a software development life cycle without formal specification are quite high, and the cost of an error as you go downstream in the process, it's more and more expensive to fix. So errors are best handled at the requirement stage as opposed to at the implementation stage, where a design might have to be changed, the requirements might have to be reread and redesigned, the specifications might have to be rewritten, and so on. So it's better to try and catch the errors up front within the life cycle, and that ends up costing a lot less during the overall development process as opposed to other methods. So what are some of the properties of formal specifications? We've talked a lot about kind of what they are at a very high level, but getting into the details of it, what are some of the properties? The first thing is the specification has to be complete, in the sense that everything that needs to be described within the user document definition will have to be carried over appropriately. The context that is required that the user might have assumed in the case of writing the user requirements document or the requirements definition document will now actually have to be spelled out. So that is what completeness is all about. It has to be consistent. So for example, there cannot be ambiguities, the sort that we saw with respect to the number of chips and the power that had to be consumed, right? The example that we saw in the last class can be carried over here. In that case, there was an inconsistency with the two requirements. One requirement being that fewer chips had to be used, which meant more chips had to get put onto one chip. That would consume a lot more power, and the second requirement was that the amount of power that is consumed by any one chip had to be lowered. So there was like a fundamental inconsistency between those two requirements, and that is what consistency here really means. Conciseness is one of the problems with natural language specifications is the verbosity, right? So requirements documents for even medium sized systems can run into hundreds of pages. It's not something that a software developer is going to take to very kindly in order to read, interpret, and then build the system using. So conciseness of the specification will come into play automatically when you're using formal methods or mathematical notations. In fact, that is one of the byproducts of using these kinds of notations. Unambiguous, which is kind of related to the consistent property. Executable is an important property, and this forms the basis of transformational development that we talked about a few minutes ago. Essentially, a lot of the specifications written in the languages that we just saw, large, Z, VDM, and so on, are directly executable. What does that mean? It means that designs can be generated from these specification documents. The designs can then be turned into code automatically if the designer gives the green signal. The code can then directly be executed. So the steps going from a requirement specification all the way down to executable code are now completely handled by a machine as opposed to humans getting involved in the process, and that is the holy grail of software development in any case. The other important property is the reusability of the specification. So if a specification, for example, has been well written for, say, a performance requirement, that the response time of a particular call to a module, software module, shall not exceed 50 milliseconds, right. That is a specification of a non-functional requirement, and that specification might be applicable in a variety of cases, right. It can be applicable in the construction of a website, can be applicable in the construction of a control system that is driving some kind of a process industry, let us say the chemical industry, and so on. So, in each one of these cases, right, this piece of specification that was written out for some other system can be reused as is without having to change much in it. And in that case, so you cannot, however, reuse natural language specifications. You will simply have to cut and paste it into another document, but in this case the entire artifact that has been created as a specification can be reused as code, and even the code that is generated out of this at the end of the day can be reused, right. And what formal specifications tend to do is to provide a language of communication between the various people involved in the production of software. So it provides a common language, whereas the analysts, the developers, the testers, the implementers, all of them can exactly understand what is being asked of them and kind of go about their task without any clarifications being required. And like we saw, it has its basics in discrete mathematics. Set notation and set theory, Boolean logic and predicate logic are typically the techniques that are commonly used in order to specify formally some of these systems. So, having kind of seen what formal specifications are, what are some of the advantages of using formal specifications, let us try to get into a small example that will try and illustrate, we will try and illustrate some of these techniques here. The example is that of a library system that is to be constructed. The library has two sets of requirements that the library system is going to use. The first requirement is the book can either be in the stacks, that is, it is in the library, it can be in the stacks, it can be on reserve, or it can be loaned out. If it is on reserve, then it is still in the library, but somebody has asked for it, right. If the book is in the stacks or on reserve, then it can be requested by a user to be checked out. Right. These are the only two requirements. Just for the sake of simplicity, we have ignored other requirements that is commonly pertaining to that of a library system. Right. What we want to do is to formalize the concepts and statements here and prove some theorems to kind of help us get confidence that what we have written out in terms of formal specifications is indeed satisfying all the properties that we saw in a couple of slides ago, which is the notion of unambiguity, and the notion of completeness, and the notion of consistency, and so on and so forth. So, let us first start formalizing some of these concepts. The first set of concepts that we want to take a look at is the four conditions. Where can the book be? Right, and so we say that S here stands for the fact that the book is in the stacks, right. So, again, conciseness of notation, instead of having to say the book is in the stacks each time around, just the notation of using a single letter for this, namely S, is going to help us understand this. R stands for the fact that the book is on reserve. Similarly, L stands for the book is on loan, which means the book has already been given out, and Q is the book has been requested. Right. Now, the first formalization that we want to do is that the book can either be in the stacks, on reserve, or loaned out. Right. It can't be in two places at the same time, is what we are trying to say. Let us see how we can formally denote some of this. The first thing that we are trying to say here is that the book is in the stacks, which means it is S, and this notation stands for AND, S and it can't be, if it is in the stacks, then it can't be on reserve or on loan at that point in time, right. So, somebody has not put it on reserve, it cannot be loaned out. That is what R or L stands for, and that is how you read this particular notation, and this sign stands for a not, right. So, if it is in the stacks, then it cannot be on reserve or on loan. That is what the notation S and not of R or L stands for in this particular case, right. Similarly, what we are trying to see here is that the next set of specifications try to say that it is on reserve implies, which is what this is, it implies that it is not on the stacks, which means it has been brought over to some library counter somewhere and kept ready for the person who had requested it, neither has it been loaned out, right. Similarly, the last specification essentially stands for L and not of S or R. What this means is, if it is loaned out, then it can't be on the stacks, neither can it be on reserve, right. So, this is the set of specifications, this is a formal notation for indicating that the book can either be in the stacks, on reserve or loaned out, but not any two at the same time, right. The next bullet here is essentially trying to indicate, talk about how the book can be requested. Now, the book can be requested if it is either on the stacks or it is being held in reserve for the person who is requesting the book at that point in time, and that is what this is trying to say. The book is being requested. Remember, our notation Q stands for the book being requested, so and L stands for the book being loaned, and there is a differentiation between the two states. So, Q implies S or R in this particular case, right. So, if the book is either on the stacks or it is on reserve, then the book can be requested. That is the implication of this particular notation. So, what we are seeing here is a way of concisely putting together a mathematical notation around certain concepts that are pretty familiar to us, right. If you take a look at the English language specification of this, they are fairly familiar concepts. The notion of libraries, the notion of books being on stacks or on reserve, the notion of loaning out books or checking out books, and so on and so forth. Now, what we have gone and done to the set of natural language specifications or English specifications is converted them into a formal notation, which we can then use and manipulate for some program proving concepts or from theorem proving concepts. We just took a look at trying to put together some formal notations around the English language specifications that a book could either be in the stacks, on reserve, loaned out, etc., etc. Now, what we are interested in doing going forward is to basically write down a theorem to help validate the specification. And the theorem is going to be a pretty simple one, right. The first thing is that a book that is on loan, it can't be requested. The book is not even in the library at this point in time, and therefore, the book that is on loan can't be requested. And to put it down formally, what we are interested in proving is that to prove that if it is on loan, that is L, then it cannot be requested, which is not of Q, right. And this will help us check whether the specification matches our understanding of the software and vice versa. And the approach that we will take in this particular case is the proof by contradiction approach. And proof by contradiction is that we start out by making one assumption, right, that the statement is false is the assumption that we will make in this particular case, and then we will derive a contradiction through successive refinement and steps that we shall see shortly. Now, having derived a contradiction, since it is pretty clear that only one assumption was made, the assumption must have been false, right, because we have come up against a contradiction. Therefore, the statement must be true in the first place and it can't be false at all. So, that is the approach that we will take, and let us go down the set of steps that would now be required for this, right. If we have to prove that L implies not Q, then we will start out by saying that we have to assume the negation, right. So, we have to assume not of L implies not Q. This is the first step. Assume negation. Now, as soon as this is done, we now start refining what we have just written out, that is the negative statement that we have written out. By rewriting this implication, we can say that this automatically leads to not of not L or not Q. Right, we are simply rewriting this to say that not of not L or not Q instead of L implies not Q. Right, now by De Morgan's law, this can simply be written as L and Q. Right, and simplifying L and Q, we simply end up at L in this case, right, and L, because of the biconditional that we had, that is, remember the first set of notations that we had, right, L and not of S or R, right. So, because of that biconditional, L will simply end up implying not of S or R. The biconditional that we had was L double implies not of S or R, and we had this before. Right. Now, continuing on, so the not of S or R implies Q by simplification, right. Q, however, implies S or R, right. The fact that a book is requested implies that, and this was one of the original definitions that we did, the fact that the book was requested implies that it is either on the stacks or it has been requested, right. It's on reserve or on the stack, sorry. So this implication is by the definition that we did earlier, right. So this is a contradiction. On one step we have not of S or R, on a few steps later we have arrived at S or R, which is a contradiction. Hence, the assumption that we made in the beginning of this entire theorem must have been incorrect. The assumption that we made was not of L implies not Q, and this is incorrect because of the contradiction, as a result of which L implies not Q, QED. So, what this example which we have kind of gone through in a fairly detailed manner is trying to show is the fact that a formal specification such as what we just wrote out for a very simple library system with just 2 rules can be used to prove certain properties of the system itself, right. And in this case the rules were pretty simple, that the book can only be in one of 3 different states, that it can either be on the stacks, it can be on reserve, or it can be loaned out. And the second thing that we saw was that the book can be requested only if it is on the stack or it's on reserve, that is by that definition we naturally came to a theorem which said that if it is loaned out it cannot be requested, which is L implies not Q, and we said let us see if we can try to prove this, and we indeed can prove this just based on the notations that we have set out for ourselves, right, and the definitions that we did at the beginning of this little exercise. So what formal specifications give you is now you have the confidence that the specifications that you wrote out of the system in the beginning of this exercise is something that is correct, right. Correctness is one of the properties, if you remember. It is very concise. If you look at the specification, it is hardly anything in it, and it's clearly pretty consistent, because any inconsistent statement such as the one that we just made can be proved to be incorrect, and so on. So it satisfies all the criteria of the formal specification. At the same time, it gives you the confidence that what you have written out in the specification is something that you can go forward with in order to construct the system from it. Right. So there are different kinds of specifications, even though there are different models based on which specification can be done. Each one of these models can be applied to each one of the specification types that is being shown on this slide. The two kinds of specifications are interface specifications, which basically just tell you how subsystems are going to interact with each other and not about the details of a particular subsystem by itself, and behavioral specifications, which primarily focus in on the behavior of an individual subsystem or of an individual component of an individual module and so on. So, it does not concern inter-component, inter-module or inter-subsystem relationships as much as it is concerned with the internals of a single module by itself. So, interface specifications are largely large systems. Typically the way they are built is they are decomposed into a set of modules. It is called the process of modularization, and each module has a well defined interface between just like every other module does, and the interaction between any two modules is purely on the basis of this interface. Nothing else can be assumed about this particular module. How it is built or how it does what it claims it is going to do is none of the concern of an interacting module, whereas it only bothers about the interface specification, and it is only concerned, interface specifications is only concerned about three pieces of information. Interface specifications primarily deal with the operations, and for each operation it deals with return type of that operation. In other words, what is the type of the output that can be expected of that operation, what are the different parameters that the operation ends up taking, and of course, what is the name, how do I end up calling the operation by itself. So, every module or a subsystem within a software specification is made up of multiple such operations, and the sum of all the operational specifications that we wrote out is the interface specification. Right. So, interface specifications can be seen in various forms. If you took a language like Java, for example, interface specification was simply Java interfaces, right. These kind of explain what is the name of an interface, what are the different methods that belong to this particular interface, and for each method what is the return type of the method, what is the name of the method, what are the different parameters, what is the order of the parameters that it takes it in, what are the types of different parameters, are there any other types that can be substituted for this type, and so on and so forth. So, the obvious advantage of these kinds of specifications is the fact that individual subsystems can be specified separately, and the development of each one of these subsystems can now go on in parallel by different developers, whereas the specification of all the individual subsystems and how they interact with each other is typically done by the system architect, but then development can now go on in parallel, and that is one of the big advantages of these methods. Right. The interfaces can be defined as abstract data types. Now, in order for these specifications to be formal, some level of behavioral specification also needs to be added, which when you combine interface and behavioral specification, you get what are known as abstract data types, and we will go into the details of abstract data types and how to construct them and what are the formalisms surrounding them in the next lecture. And the algebraic form of specification that we saw earlier is obviously very well suited for interface specifications, because it does not concern state, right. Interface specifications are not concerned with state either, and we saw that in the case of model based specifications it was an interaction of the state and the operations that can be defined only on that state, whereas here it is very different. So, we have kind of gone through this diagram, which basically says that different subsystems, there is two subsystems A and B, and in the case of each subsystem is represented by a set of interfaces, which is simply diagrammatically shown this way, and it shows that if the two subsystems end up interacting with each other, then it can only call methods or operations on the other subsystem in a predefined way. Behavioral specifications, on the other hand, algebraic specifications can end up becoming quite cumbersome. right, when the object operations are not independent of the object state. The other thing is that simply by specifying the set of operations, it is not going to be enough. What also needs to be specified are certain constraints on behavior that these operations can end up invoking in terms of the internal state of the object. So, for example, any kind of arbitrary state manipulation is not going to be possible. To give a good example, if you consider a stack, which is a data structure that is used almost every day in computer science applications, the stack has 4 operations to it, right? It can you can create a stack, you can destroy a stack, you can pop an element off the stack, and you can push an element onto the stack. 4 very simple operations of that of a stack, and one of the conditions or the constraints that has to be imposed as far as the stack is concerned is that you cannot push something onto a stack that is full, right? Another condition or constraint that can be imposed is that you cannot pop an empty stack. You're not going to get back anything off of that, and it's an illegal operation to be done. Now, and what is the result when you pop a stack that has just been pushed with an element, for example? That's a kind of behavioral specification that is not very well done with respect to the interface specifications that we just talked about. It's very incomplete, as a result of which you would also need certain constraints on behavior which will be put forward in abstract data types like we will see in the future. The other thing is that model based specifications end up exposing state, and all the operations are defined only in terms of changes to the state, and the Z notation, like we saw earlier, one of the languages for expressing model based specifications is Z and VDM, and Z is a fairly mature technique for model based specifications and uses highlighting etc. for presenting the specifications themselves. So, some of the key takeaways as far as this introductory lecture to formal specifications goes are: formal system specifications complements informal specification techniques. So, although the wish is that you can go from a requirements definitions document which is written by the user, remember, to a design really going through formal specifications, it is almost always appropriate for you to try and write down the natural language specification corresponding to this requirements document. The natural language specification can then be given to an expert who is well versed with the mathematical notations, who can then come up with a more formal specification. So, they end up complementing informal specification techniques. Also, the other thing to consider is that almost invariably the entire system cannot be specified formally. So, you will have to take the critical parts of the system and then make sure that these are the parts that need to be absolutely foolproof. These are the parts that cannot undergo any error whatsoever. So, for example, the part that does the test firing of a rocket on the space shuttle, right? Things like that would have to be specified formally, whereas the rest of the system is typically just specified using natural language or informal specification techniques, and then the two come together and complement each other very, very well. Formal specifications by their very nature are unambiguous. They are very, very concise and precise, and they remove areas of doubt in a specification. So, if you take a look at the natural language specification, and if a particular piece of specification is open to multiple interpretations, this is another place where formal specifications can be used. And they force the analysis of the system requirements at a very, very early stage. So, whatever errors or inconsistencies or lack of completeness that exists within the specification is caught at a very early stage in the process, and like we have seen before and like several studies have proved, catching errors at an early stage is extremely beneficial. They cost a lot less to fix when they're caught up front, as opposed to when they're caught in the tail end of the process, where the design might have to change, the implementation would have to change, and so on. And so they're obviously most applicable in the area of critical systems development and standards in this area. Algebraic techniques and model based techniques exist. They are the two kinds of formal specifications. Algebraic techniques are primarily focused on the interface, whereas model based techniques are primarily focused on the state of the module which is being specified. They revolve around the state, whereas algebraic specifications revolve primarily around the interface specification. And we shall see an example and some of the detailed techniques that can be used to develop abstract data types, which are really algebraic specifications, a form of algebraic specifications, in the next lecture. Thank you.